I want to start with Faraday's law of induction, and I think it would be good practice for you to write it down. You ought to take every opportunity you have to say, do I remember all the stuff I'm supposed to remember? So I presume you have started the show again because you have written it down, and you may have written this, and you may have not included the N, but that the rate of change in magnetic flux gives rise to the EMF. Now, will you please stop the show and write down an expression for magnetic flux? I presume you have started again, and hopefully it looks like this. So it could be that B is a function of time, or A is a function of time, or it could be that the angle between B and A, that is the most typical situation, is a function of time. Or it could be that multiple are functions of time, and you would deal with that in getting the EMF. Now, I want to consider this, pull these out so we can see them. I want to consider this picture from the book where this hand is pulling the wire out of the this region of magnetic field. Only inside the dotted lines is there magnetic field, that out here in this pure blue there's no magnetic field. So the flux through this loop is changing as a function of time. That B is staying constant, but the area that has only goes over to here, that has magnetic field through it, is changing as a function of time. Theta is constant. And it would be well for you to take this opportunity to confirm that you got the current in the right direction. And what instead I've done on your worksheet is given you a different scenario where you could practice getting the current right. But for this particular situation, the flux being equal to this quantity, that B and A always being parallel or anti-parallel to one another, I don't think it matters particularly, but we can just drop the dot. B is constant, I can pull it outside the integral, and so you get this area here times B, but the area is going to be equal to L, and this distance here, x, and then we take the rate of change in the flux, that value that you just got, and the rate of change in the flux, well, B and L are not going to change as a function of time, so they just stay constants, and you have the dx dt, but dx dt is equal to that value V, with which you are pulling it out. Okay, I'm with you on that. The current would be a matter of taking the EMF that's being generated by that changing flux and dividing it by the resistance of the loop. So I can take this quantity and put it over R. Then the force is going to be this cross product of the current and the magnetic field. That this is the force here along side 1, and so you have the current flowing there, which we just got was equal to this quantity times LB, and that negative is only going to affect the direction that the current flows, so I've left it out. Current times L times B, bing bing. And so we could stop with that ugly expression, but I want to do something else cute, and that is that I'm going to look at the power Oh, and before we go there, let me point out there is this force from this section here. There's also force from these two sections, but they, having equal length and equal current, are going to have equal forces, and so the net force there will be 0. And on this fourth side, F4, there would not be any force because there is no changing, there's no magnetic field. Yeah, there's current there, but there's no magnetic field that the current is running through, so there would be no force on that side of the wire. At any rate, back to power, which in the case of constant force and constant velocity could be written as F times V. And then for F, I will put in this quantity, simplified a little bit. And then this V means another V times that, so you get a V squared. And then I'm going to change this so it's all of these squared quantities over R squared. I'll multiply and divide by R, so I end up with an R squared on the bottom, and I can write this whole thing squared, and then times R, and that's I squared R. And that should look like a familiar result, that the rate of thermal dissipation of energy is going to be equal to the current squared times the resistance. So that's always very affirming to get a familiar result out of what you have done. Here is a checkpoint for you to do, and I expect you to do a great job with it. Now, this is very interesting. Here in this first scenario, what you have is a region of magnetic field. Only inside of the yellow is there magnetic field. It's pointed away from us. And then we have this copper ring sitting in here. And as a result of changes in this magnetic field, changes in the flux through this copper ring, there's an EMF pointed as indicated by the arrow. There is a current flowing as indicated by the arrow. Well, based on that, I would like you to tell me whether this magnetic field is getting stronger or weaker or staying the same strength. And then they go on, and it's the same exact scenario, except this time it's not a copper ring, it's just a circular path. There is no thing there, at least no thing that conducts electricity. Oh no. There is no thing that, yeah, we're okay. So this time there will still be changing flux through this loop, and so there will be EMF, but that EMF will not result in a current this time. But what the EMF will result in is in an electric field, pointed in the direction that a current would have gone if there had been a conductive pathway. And of course, our understanding of current is that it's an electric field moving through the conductor. Now, the book goes on to look at the electric field. And the book only did the electric field inside of the yellow region. I don't know why they didn't do the electric field outside, so I have labored greatly for you to create an image of the electric field outside that you want to think about various size loops. And inside of this loop, there would be the rate of change of flux. I need some help. Okay, let's take this expression. Yes, Okay, so the rate of change of magnetic flux gives rise to the EMF, or we can write that EMF as think of it, voltage is equal to negative of field dot the distance that you have moved through the field. I don't think the negative belongs there though. So instead of writing EMF is equal to this, here is a better form of Faraday's law, and it's going to be the field dotted with the distance. Now, as we increase the R here inside of here, the area, yes, the area is going to get bigger as the square of R, and so the flux is going to get bigger as the square of R, and I think the rate of change in flux is going to get bigger as the square of R. So you would think that the field would get bigger as the square of R, but it's field dot ds. You want to go all the way around this loop, and the circumference of that loop is going to get bigger directly as R, so I would expect the field to get bigger as R. In fact, I would expect the field to get stronger in a direct proportion to R. And I hope that is what you see here. As the density of the field lines gets greater and greater, that the field strength is getting greater and greater as R gets bigger. And then when you get outside, of course the only place where there's changing flux is here in the yellow region, and so the flux is not going to, the rate of change in flux is going to be constant for all of these circles out here, but it's still going to be the case that the ds, the trip around these arcs, is going to go directly as R, and so E would have to get smaller as R. That out here, I would expect E to be inversely proportional to R. Oh, what brilliant reasoning I have done. And then finally, they give you this problem with these little avocados. And they would like to ask you some questions about them. And here, so would I. Here is the first question. Here, let's just get this out of here. Oh, here was a little development I was supposed to do to get you up to feeling comfortable with replacing EMF with that. All right, cool. So I would like you to answer this question. Who has the greatest change of flux? And who has the greatest EMF? And then also this question, I would like you to compare the EMF at 3 and at 4. Okay, that's the EMF around a loop. Okay, now here we have two pictures of electric fields. One of them is produced from charges, static charges, and the other is produced by changing magnetic flux. And you ought to be able to tell which is which. Now, let's consider this statement of Faraday's law of induction, and let's take a little trip. Let's start at A and go over to B, and there my path, my ds, is going to be in the same direction as the field. So when I get the dot product, I get a positive there. And if I've done this right, right? We used to have this statement that V was equal to negative E dot ds. And now that was last year, and this year it should be this. Not ds, it was s last year. This year it's ds. So I think there should be an extra negative here. I'm very uncomfortable about that. I don't think there should be an extra negative that would sort of cancel that one out. Yeah, I don't know. Let's just say that this is good reasoning. And so if ds and E were in the same direction, then you would get a positive dot product, and that would mean that you were going to a lower voltage, that B was at a lower voltage than A. And then if you continued your trip and went back to A, going in that direction, here you would be drawing contrary to the field. And so there you would get the opposite effect. If here you were going with it and you had a loss of voltage, here you would have a gain of voltage. And when you got back to A, the net change in voltage would be zero. That the potential difference between A and itself would be zero. And suppose you went from A to B, dropping voltage, and then you went back from B to A this way. Again, traveling contrary to the field. But this is a weaker field out here, and so even though it is a longer path, your ds is bigger, the field is correspondingly weaker, and when you got back to A, the potential difference between A and itself would have to be zero. It only makes sense. However, let's do it over here. And if you start at A and go over to B, why there I was traveling contrary to the field, so that would be a gain in voltage when I got to B. And then if I went back to A again, this time the trip back was also going contrary to the field, the electric field. And so again there is a gain, that to go around this loop is to end up at a higher potential when I get back to A again. That the potential difference between A and itself is not zero. And if I went around a second time, it would be even a new value. That's nonsense. And how do we deal with that being nonsense? And this is the way we deal with that being nonsense. We make some notation on the side of our map, and that says, here be dragons, don't go there. We just say electric potential is only going, that V is only going to have meaning for electric fields produced by static charges. There's the answer to your question at the beginning. And for electric fields created by changing magnetic flux, we're going to say that electric potential has no meaning. Well, that's pretty disappointing. And my friends, when we deal with an inductor, we are going to talk about electric potential in a situation where it is caused by changing magnetic flux. Well, make up your mind. No, I can't. I've gone all crazy. All right, so here's a problem for you. We have this yellow region has a magnetic flux which is changing at a rate of 10 teslas per second. Notice that the magnetic flux is going away from you, so if it's a positive change, I think that means is the flux going away from you is getting weaker, and that eventually it'll reach 0, and then it'll start becoming flux towards you at a rate of 10 teslas per second. And so for the region inside, this radius of the magnetic field is capital R. So for some point inside, like this black indicates, what is E at each R? And for R outside, what is an expression? When you get out here, what is expression for the electric field at every new radius R? And then you take that and you graph it. And it should be a pretty non-surprising result, but you got to get your head wrapped around it. And that's a good thing, to get your head wrapped around it. So start wrapping heads.